Welcome to the Explainer. Today, we're diving straight into the ultimate translation device used by chemists to literally decode the microscopic universe. We're talking about the mole concept. It's the fundamental bridge that connects the invisible world of atoms to the macroscopic world we can actually touch, measure, and see. It's kind of a wild problem when you think about it. Chemists deal with trillions upon trillions of invisible atoms in every single reaction. So how do they know exactly how much of a reactant to pour into a beaker to get a specific product without just blindly guessing? I mean, you can't exactly take tweezers and drop a single atom onto a standard lab scale, right? We need a way to count the uncountable. Here's our roadmap for today. We'll look at the chemist's secret dozen, Avogadro's massive number, the micro to macro bridge, calculating reactants and products, and finally, avoiding common calculation traps.
All right, Section 1, the chemist's secret dozen.
Let's demystify them all. You see, it's not some incredibly complicated mathematical formula. It's actually just a really simple, practical grouping concept. Think about everyday language. When we say a pair, we instantly know that means two things. When we say a dozen, we know it means 12. Well, a mole operates on that exact same logic. It's simply a word used to describe a specific number of things. The only catch is that, because atoms are so minuscule, the number of things a mole represents is exceptionally large. So, where a baker uses a dozen to group 12 eggs for a cake, a chemist uses a mole to group 6.022 times 10 to the 23rd atoms or molecules to run a reaction. It's really just a standard set, you know? A convenient grouping that lets scientists talk about collections of identical, incredibly tiny objects in a way that actually makes sense practically. Moving right along to Section 2, Avogadro's massive number. Understanding exactly how many items are in this chemist's dozen is absolutely crucial. This massive figure is called Avogadro's number, named in honor of the Italian scientist Amedeo Avogadro. Get this. 1 mole equals approximately 602 sextillion elementary entities. That is a 602 literally followed by 21 zeros. It's a number so outrageously huge that our brains honestly struggle to even comprehend it. But in the chemistry lab, this mind-boggling number is an absolute necessity. And why is that? Well, because atoms are unimaginably tiny. If we actually want to create a lab-scale sample that we can see, hold, and weigh, like, say, a small splash of water in a beaker, we need this massive Avogadro's number of molecules. To put that into perspective, it takes a full mole, so 62 sextillion molecules of water, just to give us 18 grams of water, which, by the way, is only about a single tablespoon.
Next up, Section 3, the micro to macro bridge.
Okay, so we have this massive number, but how does it help us practically? The core trick that makes this whole concept tick is molar mass. Because of how the atomic mass unit and the mole were defined around carbon-12, the mass of a single element on the periodic table, in atomic mass units, or AMUs, is the exact same number as the mass of 1 full mole of that element in grams. It is a brilliant little shortcut. Let's put that definition to work. By using molar mass, we can glance at the periodic table and immediately know that 1 single atom of carbon weighs 12 atomic mass units. And because of our shortcut, that means 1 mole of carbon atoms weighs exactly 12 grams. Meanwhile, heavier elements have a higher molar mass. 1 mole of lead atoms weighs 207 grams. It's the exact same number of atoms, 1 mole, but drastically different masses, simply because the individual atoms themselves weigh more. So the really crucial takeaway here is that the mole acts as the ultimate translation bridge. It lets us step right out of the microscopic world, where we measure in atomic mass units, and cross over into the macroscopic world, where we measure bulk mass in grams. If a chemist weighs out a specific number of grams of a substance, they can use this bridge to know exactly how many microscopic atoms are sitting right there on their scale. Pretty neat, right? This brings us to Section 4, calculating reactants and products. With our bridge solidly constructed, let's explore our main focus for today's explainer, stoichiometry. This is exactly how chemists use the mole concept to calculate the exact amounts of reactants and products needed for chemical equations. Think of a balanced chemical equation exactly like a baking recipe, but instead of cups of flour, you're using moles. The coefficients, the numbers in front of the molecules in a balanced equation, tell you exactly how many moles of each reactant you need to yield your product. If an equation says 2H2 plus O2 yields 2H2O, that means exactly 2 moles of hydrogen gas react with 1 mole of oxygen gas to produce 2 moles of water. It's a perfect proportional recipe. But remember, we can't measure moles directly on a lab scale. We can only measure grams. So to figure out how much product you're going to get from a specific mass of reactant, you just follow 3 simple steps. First, divide your starting mass in grams by its molar mass to convert it into moles. Second, look at your recipe, the balanced equation, and multiply by that mole ratio. Finally, take those product moles and multiply by the final product's molar mass to convert back into a tangible weight in grams. Mass to moles, moles to moles, moles to mass. Simple as that. This table neatly summarizes the core conversions you'll use constantly in the lab. When you need to translate between the mass on your scale in grams and the chemical amount in moles, you use molar mass. And when you need to translate between the number of moles and the literal count of individual microscopic particles, you multiply by Avogadro's massive number. Honestly, these are the formulas that completely unlock quantitative chemistry.
Finally, Section 5, Avoiding Common Calculation Traps.
Now that we know how to do the math, let's wrap up by looking at the number 1 trap that trips up students and professionals alike. According to chemistry educators, a major high-frequency pitfall is just totally forgetting to check the chemical recipe. People will calculate the moles of their starting reactant and then blindly assume that those moles will automatically make the exact same number of moles of product. They just assume a simple 1-to-1 ratio without ever actually checking the coefficients in the balanced equation. And chemistry tutors warn about this constantly. Think about it. If your chemical recipe says it takes 2 parts reactant to make 1 part product, and you blindly assume a simple 1-to-1 ratio, well, your final answer is going to be completely doubled. Your math will be wrong, your predicted yield will be wrong, and in a real-world laboratory, your entire chemical reaction could literally be a costly failure. So always, always check the recipe. And there you have it. By understanding the chemist's secret dozen, Avogadro's massive number, and the sheer power of molar mass, you can now seamlessly cross the bridge between invisible atoms and tangible grams. You possess the power to connect the invisible dust of the universe to the physical objects right there in your hands. So, looking at the world around you, what chemical mysteries will you translate next?